All right, so now we move on to lesson 9.1 part 2, and that's linear equalities in two variables, primarily dealing with the calculator, so typing these things into our calculator and being able to sketch regions. And then second of all, we're going to deal with lots of application problems for the second part of this part 2 lesson. So let's kick it off with the following. Now, on our calculators, we have the ability to put inequalities in the following way. We know from the previous lesson that in order to type this into any sort of calculator, whether that be quad equations unit, or I should even say quad functions, if we want to type any of this stuff in, what we must do is we must isolate one side to be y. So we're going to take the inequality and isolate it so that on the left, or I mean even the right, but let's make it the left-hand side, we want the inequality to have the y all by itself. Now, in our calculators, what we can do is we can actually set it so that it is going to be matching to one of these inequalities such that it visualizes this for us. If we want to do the less than or equal to or less than, we must on our TI calculators put in the bottom triangle here or the lower region triangle. To do this, what we're going to do is we're going to shift our cursor over to the left-hand side of the Y1. And on the left-hand side of the Y1, what you can do is click enter until you see this lower region. Now, if you have the Casio, what you'll have to do is you'll have to click on your graphing menu or your Y equals mode, but primarily your graphing window. Then what you're going to have to do is you're going to have to type in type. Once you type in type, what you can do from there is you can select the function to be either a less than or a less than or equal to. You can do all of this stuff right from that type and then click arrow over. From type arrow over, you can select it. And then for my CAS or for my TI users, we go back to if you want to do the upper region, you do the same thing. So you go to the left of that Y1 and then just click enter until you see this piece here or that upper region selection. Now, what this does is it creates a shading. And so once we know that we can shade certain regions, then our graphing calculator can actually show us what regions are included. Now, this isn't necessary because if you actually understand the inequalities and what's going on, you can actually shade these things for yourselves, especially if you're doing your own practice problems. But this is a way in which we can do this on the calculators. And again, for the Casio users, you're going to click type arrow over, which is the last key on the top right, and then it should give you some options to type in where your function can be one of the following options here, or your inequality, because we're not in the functions unit, our inequality can be one of these. Now, if you need help, let me know. Okay, now in terms of graphing linear inequalities on the TI Inspire, that's going to be a little different. It's a little nuanced. If you would like to go through this, go through this if you have the Inspire. For lots of you, you don't have the Inspire, so you don't need to worry about this. Inspires are one of the more rare calculators. People do have them, but if you do have one, follow these instructions to graph your inequality. All right, now let's go on to the calculator examples. So typing these things into our graphing calculators, we know we must have the y equal to or the y on one side, just like we did in quad functions and even equations sometimes where we had to make sure everything was on one side such that the y was isolated. What we're going to do is we're going to do the same principle here. So first and foremost, I'm going to start by subtracting x from both sides. When I subtract x from both sides, I get 4y is less than negative x plus 30. Now what I'm going to do is divide both sides by the 4 in order to isolate this. When I divide both sides by 4, this is going to give me y is less than negative 1/4 x. I'm just going to put the 1/4 out front, and then plus 30 divided by 4, this is the same as 15 divided by 2. Now, you could put decimals for both of these for the inequalities unit. That would be okay, but if we can keep them as fractions, why not? We'll keep them as this. Now, as you notice, the inequality did not flip, and that's because we did not divide by a negative or we didn't multiply by a negative, so just be watching for that. Now, when we type this into our graphing calculators, we're going to type in y is equal to, or y1 is equal to negative 1/4 x plus the 15 divided by 2. Now, if you have the TI calculator, because we want it where y is less than, we want it such that it is the triangle that includes the lower region. So off on your left-hand side of the y equals, you're going to arrow over to it by clicking left. You're going to click enter until you see this lower triangle. For my Casio users, you're going to click type, arrow, or the right arrow. And then what that's going to allow us to do is then get into the menu where we can select the less than key. Now what we're going to do is I'm going to give you some window settings to type in. First and foremost, for the x, we're going to type in negative 10, 30, and a scale of 1. For my y, I'm going to type in the following window settings. We're going to type in for our minimum, negative 5, our maximum 10, and then our scale 1. We try not to mess with the scale if we don't have to because sometimes messing with the scale can throw us off and just add some complexity we don't need. There we go. So here's what our graph should relatively look like here in terms of the overall window that we would see. Now what we want to do is we want to draw our line across this. So I'm going to take a sketch and just draw it very, very roughly in terms of what it might look like on our graphing calculator. This is approximately what it looks like. I'm going to make sure I put arrows on the end. And then the one thing we got to be very careful with this is it a dotted line or a solid line? Because the inequality, if we go back up to our inequality, is strictly less than or it's less than, we see this as it must be a dotted line because the boundary line is not equal to, it's strictly just less than. So I'm going to go with my eraser and just go one by one down the line here and just kind of put a dotted approach to it. And then again, maybe I'll just make sure I don't cut that piece off. And then maybe I can go back to my eraser and just do like small section. There we go. Perfect. So dotted line. There we go. Now we need to discuss if it's shading above or below the line. For you, you have to look at the inequality and say, well, where are the y values below the line? Or where do we say it's technically below this boundary line? It's right here. We're going to sketch all of this here. And I'll be very careful not to sketch the line itself because if it's not included, we don't want to have that within our solutions. So if you just shade with your pencil below this line, or if you take a highlighter and you kind of shade this bottom region here, perfect. All right, let's repeat this a couple more times. So we're going to go over to our next example. This one includes decimals, no problem. It's the exact same type of solution. We're going to start by subtracting our 3.6x from both sides. So minus 3.6 minus 3.6x. What we're also going to do is minus the 30 away because we also don't want this 30 attached to the left-hand side. So this is going to give us negative 5.3y. And then on the other side, it will be, because the less than is in this orientation, we're going to keep it like this. 3.6x on the other side, 4 minus 30 is negative 26. Then we're going to divide both sides by the negative 5.3. And again, what did we say when we divide by a negative? It flips the inequality. So I'm going to see that this inequality that was originally a less than now transforms to be y is greater than. And I'm going to use an arrow to point down to this to indicate this. We did this in class a lot. We arrow down from the inequality and we say it flipped. Therefore, a negative 3.6 divided by a 5.3 is going to give us 0.679, and that has an x with it. The negative 26 divided by negative 5.3 gives us positive 4.905. Okay, now we know that the y is going to be greater than, or the inequality is defined where y is greater than this boundary line. We need to type it in the following way in our calculator. So our decimal will be 0.679x and then plus our 4.905. What we want to do is make sure that off on the left-hand side of the y equals, we have the shaded upper triangle, or in this case, we want the upper triangle because it's greater than. So I'm going to make sure I kind of sketch the little triangle that you should be making sure is in your calculator on the left-hand side of the y equals. On the Casio, type, arrow over, and then from there, you'll be able to select the greater than for this given inequality. Now what we want to do is we want to set some windows here. So our window for x will be x, and then our minimum is going to be negative 10, 10 for max, and then 1 for scale. Our y will be the negative 10, 10, and 1. Now, as some of you are probably looking at this, it's just the regular window settings. So if I draw my graph, it's going to look like just the basic graph. Kind of looks like it's even in terms of the up and down, even to the left and right. Now what I'm going to do is sketch a boundary line here. On my boundary line, I know that it's going to be dotted because it was strictly greater than based on this. So now I'm going to put an arrow representing, or I should say a line, representing what happens with this inequality, or the boundary line that is defined by this inequality. We need to make sure it's dotted. Reason it's going to be dotted, or it's going to not be completely shaded in, is that we know it is strictly greater than. And if it's greater than, we say that greater than is all the values above the boundary line, which is here. So we're going to shade, and we're going to be very careful about the boundary line again, because I don't want to shade necessarily on the boundary line. If I shade on the boundary line, that kind of seems like I'm telling you that that is applied here. So I'm just going to use enough shading to kind of fill that in without actually touching the boundary line, just to avoid confusion. There we go. So the inequality will be satisfied for all values that are in this green region. Okay, now final example. We scroll up and we see another example with decimals, no problem at all. So what we're going to do is first of all subtract the 6.59x from both sides. If I subtract the 6.59 from both sides, then this is going to give us on the left-hand side 10.79y. is less than or equal to, we keep the orientation as is. This is going to be negative 6.59x plus 130. I'm going to divide both sides by my 10.79. So divided by 10.79 divided by 10.79. By doing so, here's what my inequality becomes. Y is less than or equal to. Do you notice how I kept the inequality in that same direction? It's because we divided by a positive and not a negative. Now we continue this on, and it's going to give us negative 0.6107 for x. And then for the y value, it's going to be positive 12.048. Okay, let's put this down for our y1. Our y1 is going to be the negative 0.6107x. And then our y-intercept, or the constant value, is 12.048. In this situation, it's less than or equal to. So on the TI calculators, you want it where the lower triangle is shown on the left-hand side of the y equals. For my Casios, you want to go type, arrow over, and then make sure it's less than. Now I'm going to give you some window settings we can type in here. So below, here's our window settings. We have x, where our x minimum is going to be negative 10, 10, and 1. So we don't actually adjust our x's. Our y is going to be where we have it as negative 5, 20, and 1 for the scale. Now, this is going to give us a graph that kind of shifts up a little bit vertically, but stays the same in the x. So it's going to be divided perfectly left and right in terms of x, but just a little bit shifted up. Our arrow for this one, or our boundary line that we're going to use to define this, is going to start up in the top left, kind of come down, and then approach here. And it's a little bit flatter than that, something like this, based on this. Now we're going to put arrows on the end here. And then again, we're going to decide, is this supposed to be a dotted line or a solid line? It's definitely solid because the inequality included the value. We see that there is an equals on the inequality, so it includes the boundary line. And then we just got to be very accurate and say, where do we shade? In this case, it's less than or equal to the boundary line, so it's going to be below this boundary line. And I'm okay to highlight the boundary line. I might just do a little bit below just so I don't cover it up, but there we go. So that's my boundary line. And then every value that is below is technically counted. So all of the ordered pairs, or all the solutions in the green region, would all be considered to be appropriate for this inequality. All right, let's flip over our page here. Now, here's where we go into the economic problems, which these are what I like to call economic trade-off problems. So we're actually going to make a note about this right away. At the very top, I highly encourage you throw this in. Note, we're going to say the following about all of these application problems that you're about to face. In the economics problems, these are what we like to call trade-off problems. Now, what I mean by trade-off problems, as one good increases / object increases, the other will decrease. There we go. So trade-off, because in order for one to go up, the other must go down. And there's this constant fluctuation between, do I produce or do I make or do I use one thing more than another? And so there's this constant trade-off between two things. That's the very approach that we're going to take on this thing, is that we're considering two variables that are in constant trade-off with one another, and they'll help us define it. Now, all of these next examples are actually going to be very formulaic in terms of their approach. First and foremost, let's go look at example 1 and see what this formulation will look like when we put it all together. So write an inequality to represent all possible combinations of tile and stone that can be used to make a mosaic, where the tile costs $2.50 per square foot and the stone costs $6 per kilogram, and the budget for the overall mosaic is $150. Now, when they say the budget like this, they're essentially telling you the maximum that they could spend would be this. So this is the maximum budget, if we want to use that terminology. Okay, if we have a maximum budget, this helps define the constraint in the problem. So what we're going to do below is, before we move into what this looks like in terms of the overall inequality, let's just make sure we define our variables. That's really important. So we're going to make our tile one thing. So I'm going to highlight this in yellow. Tile is one thing. Our blue, which is our stone, is our other thing. We want to define this in variables. Let x be the amount of tile, and then we're going to let y be the amount of stone. Perfect. If we define these clearly, now what we know is when we build out our equation in terms of x and y's, we have a definition of we need a certain amount of x and a certain amount of y, and that will build out our combination. Now, here's what our inequality looks like. First and foremost, it costs $2.50 for every amount of tile we add. And so if we add a certain amount of square footage, it's going to be multiplied by the amount of square footage we use of that tile. So $2.50 times the x, which is the amount of tile we end up using, plus the certain amount of stone we're going to use. It costs $6 for every kilogram. We don't know how many kilograms, but that is our unknown. That's the amount of stone we end up using. Supposedly, when we combine these two things together, the budget for the overall project will be equal to 150 or below, because we can only spend up to 550, including or not 550 but 150, and then anything below would be acceptable, but we definitely can't spend more than this 150. All right, when they say restrictions on the variable, well, simply put, x can be greater than 0, greater than or equal to 0, and then all real numbers past that. Y, or the amount of stone, must be greater than 0, and then once it's past that, it's all real numbers. Hopefully this makes sense to you, because if we're talking about or if we're talking about stone and tiles, you're not going to use a negative amount of tile in a project or a negative amount of stone in a project. So they both have to be defined as goods where they can be equal to 0. Like maybe you don't use any stone or you don't use any tile, but you definitely can't use a negative amount of that. Now, when we go to graph the inequality, this is really important. What you need to do is you need to isolate for y. Now, I'm just going to show that to you because I know that you can do this algebraic process as we just did on the previous page. When you isolate this inequality for y and you take this term and then bring it down and isolate it for y, you end up getting that y is less than or equal to, the first term will be 5 over 12x, and then the second piece, or the constant piece, will be 25. Now, this is really important. Right away, when you get this, what I want you to do is I want you to underline the b value, because remember, this is in essence, it's actually just a linear form. If we have a constant of a linear, it's actually the y-intercept. So just make sure you note that here. This is your y-intercept. Okay. Now that we have this and we have our inequality that represents this, this is good because, we have our overall definition that we could plug into a calculator. You have a couple options at this point. What I would recommend is, first and foremost, let's just draw out our situation in the graph. These will always be quadrant 1 problems. So you're going to have a graph where it will always be in quadrant 1 because we're not going to produce a negative amount of goods. And we're going to put y and x on our axis points. And then what we're going to do is, if we found out that our y-intercept is 25, I just want you to go up there and literally put that point right on the graph right away. So this is where we have 0 for x and 25 for y. Now, we'll explain what that means in just a second, but in order to build out this graph, to complete this, just like we're going to do in all the rest of the problems, what I'm going to end up doing is I want to make sure that I solve for my x-intercept, because if I know my x-intercept and I know my y-intercept, you can just draw a line between them and that becomes your boundary line. The other option in your calculator would be to type this inequality in, or the one that we just found, and then type in second trace 0, or if you have the Casio calculator, shift G-solve and root, and then you would find that value. Now, I'll leave that up to you, but I'm going to do this more algebraically in this case. So actually, let's do the graphical approach on this one, and then for the next one, we'll do it algebraically, just because I do want to show you both ways. So let's set our window in our graphing calculator to the following. We're going to set our x value to, let's set it equal to -10, 80, and 1 for the scale, because again, we don't want to adjust the scale if we don't have to. For my y's, I'm going to set it to -2, 30, and 1. There we go. And actually, because this is in quadrant 1, what I'm going to do is I'm just going to set these minimums to 0 and 0. The reason I'm going to set them to 0 and 0 is because, again, we said that x had to be greater than or equal to 0, and then y had to be greater than or equal to 0. So even if you put in for like -1 and -1 for the minimums, that would just show you a little bit of the negatives so that you can kind of see a little bit outside this overall graph. But in these economic trade-off problems, I always love to just make sure that we're only showing quadrant 1, because then that gives us a nice picture here. Now, if we do this in your calculator, in order to solve for that x-intercept, again, we can do the following. What we're going to do is if you have the TI calculator, you're going to go second, trace, and then 0. You'll do your left and right bounds, and then you'll end up finding that this is at 60 and 0. So the point that will belong here will be 60 for x and 0 for y. Now, if you have the Casio calculator, let's just include the instructions. With the Casio calculator, you're going to want to go Shift, Gsolve, and then root. Let's see if I have some space. Oh, I do. Okay, let's use that space. There we go. And this would give you the same value. So again, with the different calculators, you could just solve for the x-intercept. Now, what I'm going to do is as soon as you have your x and y intercept, we can actually connect these with a line, and it's going to be a solid line because the solid line says for every value or every combination of x and y, this would equal the max budget of 150. So I'm just going to indicate that here. On this line, on the line, these are all combos of x and y that equal the $150. So that's a really nice principle about this. The boundary line is exactly the maximum, and all the x and y's that you would type in would exist on this line would then equal, when you plug them into the inequality, the 150. Now in this, we want to shade the region that applies, or the solution region. The solution region that applies is everything that is underneath but greater than 0, including the boundary line. So we're just going to be very, very careful when we sketch this. We want to sketch everything in here, but we don't want to sketch anything outside because, again, we're not producing a negative amount of stone or using a negative amount of stone. We're also not producing a negative amount of tiles, so it's all the solutions that would exist here. Now, this gives us our overall problem. We have our x and y intercept, we have our restrictions, we have our variables that are labeled, and we also have our overall inequality. Now, when they say list 3 different ordered pairs of the solution, well, let's list our x and y intercepts as part of the solution because they are. When we look at our x and y intercept, first of all, with the x intercept, it was 60 and 0. That was one of the solutions. This meant that we use 60 tile or 60 square foot of tile. I should even put that here, 60 square feet of tile, and we use 0 kg of stone. For my other point that I could use, I could say it was 0 and 25, which was the y-intercept. So my project could include 0 square feet of stone for the mosaic, but 25 kilograms of stone. That would also be an option. So again, these are where the trade-offs come in. We could either use all tile and no stone, or 0 stone and I need to go back here and make this a tile, right? Because it was square foot of tile. We could say 0 square feet of tile or 25 kilograms of stone. Now, everywhere between those values, it's going to be a trade-off. We can pick realistically anything. So let's say I pick a point that exists like right about here, let's say. I don't know if this is an exact point to it, but we're going to label this as, let's say 20 for the x value. And then for the y value, I'm going to list something like, I don't know, 5. There we go. Might not be the most accurate, but we're just going to roll with it. So if this is 20 and 5, this would mean that the point within that region here, we could list it as 20 for x, 5 for y, which would mean we use 20 square feet of tile in the mosaic, and then we use 5 kilograms of stone. There we go. Now, again, we could ask you in this type of problem, how many solutions are there? There's actually an infinite amount of combinations. I could break this to any real number that exists below that boundary line and above 0 in both categories. There would be an infinite amount of points. So realistically, there's not really any wrong answer. What they might ask you to do at this point is just confirm it with your inequality, but all of these points would satisfy that inequality. Okay, now let's move on to example 2, where we're going to focus on a purely algebraic approach. So we're not going to do anything graphic. You can always follow this graphing method to solve your x-intercept and then get it that way. So this is valid, but we're going to continue forward now just doing algebraic. Okay, a sports equipment manager is making footballs and soccer balls. One football requires 4 minutes to produce, while the other which is the soccer ball, requires 3 minutes to produce. So maybe let's highlight that important information here. First and foremost, we have that the footballs require 4 minutes, and then our soccer balls require 3 minutes. The total we have to spend for both of these in production is 30 minutes. So now we want to define our variables and then state the restrictions, then state our inequality. So just like we did in the last problem, very formulaic, we're going to say let x be the footballs, and I'm just going to say football cutting because that's what they said. In the manufacturing process, they called it the cutting of the material. For the soccer ball, we're going to set that equal to our second variable. So soccer ball cutting will be our y values. There we go. Our restrictions for these, because we don't want to produce a negative amount of soccer balls or footballs, we're going to say, first of all, that x must be greater than 0. And as long as it's greater than 0, it can be any real number. The y values must be also greater than or equal to 0 because we're not going to produce a negative amount of soccer balls. And anything greater than 0, we know that, or greater than or equal to that 0, will be a real number. And again, why do they include 0? Because you can just not produce footballs or not produce soccer balls. That's also a valid option. You just don't want to produce a negative amount. The inequality. When we look at this, we're going to write this as it was 4 minutes for every football, so 4 times the number of footballs produced, plus 3 minutes times for every soccer ball produced must be less than or equal to the 30-minute maximum they have for manufacturing these things. Okay, what we're going to do from here is we want to isolate this for y. Theoretically, this would be good. We would look at this and be like, that is the inequality. That is the inequality definition for this situation. But what we want to do is isolate this for y such that we can solve for an x-intercept if we need it. I mean, realistically, we wouldn't even have to as well. We could just take this inequality and solve it. But I also do want you to have the ability to take this and then instead of thinking about it as having to, instead of just thinking about it from here and then solving for your x and y intercepts, I think having it in terms of the y being isolated allows you to see it as an inequality that you can type in your graphing calculator, but you can also determine the y-intercept right away without doing any algebra at all. Okay, so we're going to look at this and we're going to isolate it. First and foremost, I'm going to subtract 4x across, and when I subtract 4x across, the new inequality becomes 3y less than or equal to negative 4x plus 30. And let's make sure that 3 is a little neater. There we go. We're going to divide both sides by the 3. There we go. And then this will make our new inequality that we're going to place over here. Y is less than or equal to, we have negative 4/3 x, and then 30 divided by 3 will give us 10. Okay, so then there we go. Here is the inequality isolated for y. Now, again, as soon as you get it in this form, this is our y equals mx plus b, underline this and say that this is our y-intercept. It's really important because then we can put this on our graph or our drawing. So let's start by doing that. Just because we found the value, I'm going to go up here, I'm going to put a dot up here, and then call this 0 and 10, and label this as my y-axis, label my bottom horizontal axis as the x-axis. Okay, now, again, this is only one piece of building out the graph. In order to do this without a graphing calculator, what we need to do is solve for the x-intercept. To solve for the x-intercept, you could either use the original inequality, so this 4x plus 3y is less than 30, or what you could do is plug it into here. Maybe just to show you that you can use your inequality and it might be simplest, I'm going to do that. So I'm going to take the highlighted inequality, and if we want an x-intercept, we must set the y to 0. So let's do that over here. I'm going to go below and then be like, if I want to solve for, and actually let's do it off on the right-hand side here. If I want my x-intercept, then I'm going to write this as 3x, which is or 4x, which is the amount of time it takes to produce a football, 4 minutes times x, plus 3 times 0 for y, because we want the x-intercept, is less than or equal to 30. This leaves us with 4x is less than or equal to 30, and therefore we have an x, which is less than or equal to 30 divided by 4, which we know that means x is less than or equal to 15 over 2, which is actually equal to 7.5. Okay, there we go. So 7.5 is the solution. I'm going to write that over here. Here it is, 7.5. I'm going to roughly approximate is here on the x-axis, and 7.5 and 0 in that specific order. Now what we can do is we connect these with a line. So I'm going to take this and just connect these across with a line as such. And then we want to think about this in terms of where do we shade for the inequality. We must shade below the line because there was a maximum of 30 minutes. And if everywhere along the red line is technically a combination of X and Y that makes 30, then therefore we must shade below and then of course above 0 because we don't want to be producing or spending a negative amount of time manufacturing. That wouldn't make sense. So we're going to look at this thing and say, hey, it must be greater than 0 in both directions, but then less than or equal to the boundary line. Perfect. Okay, now from here, they ask us to sketch the solution region. Check mark, we've done. Use a test point to check the solution. All this means is pick a point that's in the green region, and it can even include the boundary line, and then plug it in. Now, the points that I would find would be really easy to use would be like something like this and this. You could use those points right away, but I'm going to challenge myself a little bit. If I know this is 7.5, maybe I choose something like 4 and 2, which let's say we approximate it to be down here. So 4 and 2 in terms of an X and Y ordered pair. Let's see if this satisfies the inequality because it looks to be in the green region, but we want to make sure just to double check. So we're going to go down below and we're going to plug this into our inequality. It's 4 times, I just want to double check the X value, 4 and 2. So we had 4 for X plus 3 times 2 for the Y is less than or equal to the 30 minutes total of manufacturing time. This has become 16 plus the 6 is less than or equal to 30. And then therefore from here, 16 plus 6, this will give us 22 is less than or equal to 30. Is that true? It definitely is. And therefore, we say that this is a solution. So I'm going to say, therefore, we know that 4,2 is a solution. And it's really important to use just like a small sentence or even just say that it is a solution right below, just so that we're aware. Because in the original lessons, sometimes I think I got too caught up with just being like, hey, I'll show the inequality and put a check mark. But that was just me being really quick. I want you thinking about, you got to be very clear with what happened. And to an average person, they should be able to look at your solution and be like, or look at your work and say, hey, okay, this is what they got for the inequality, but does that mean it's a solution? Yes. Perfect. Okay, now there's an infinite amount of combinations. So we could select as many points in that green region as we wanted, whatever would make this work here. Okay, now we are going to go to our third example, which is our final example for this lesson. And it deals with the same kind of problem. So an economic problem where there's a trade-off, but it follows all the same steps. We want to earn at least $300 in this investment. So I want you to highlight that. As soon as you see this language attached to the amount that they want to earn or the manufacturing time or whatever it might be, as soon as they give you that verbiage or that language around this of at least, this means that they're talking about it being a minimum amount. So this is a minimum amount. And if it's a minimum amount, then in the case of anything being a minimum amount, we know we want to be greater than or equal to. That's a really important thing to put here. So our graph is going to look slightly different when it comes to putting this together because potentially they want to earn more than $300, or if they make 300, that's okay. Okay, so we want to earn at least $300 on an investment in total interest annually. You want to do this by investing some of your money in bonds, which pay a 4% interest per annual or per annum, and then a GIC, like an investment account, that pays 5% per annum or per year. Now, when we write these things in terms of actually being able to use these in mathematics, decimals, the percentages we want to write in terms of the decimal value. So this is going to be 0.04, which is the percent out of 1. And then in terms of the percent out of 145, this is 0.05. There we go. All right. Now, if we look at these now, what we want to do is we want to define our variables. First and foremost, I'm going to let X be the amount of money that we pay into the bond or that we invest into the bond. So let's do that right away. Let X be the amount invested into the bond. Okay, and then the Y variable is just going to be our opposite account. It's going to be the amount invested into the GIC. Perfect. Okay. So we clearly defined our X and Y's. Let's state some restrictions. Well, we clearly don't want to invest a negative amount of money in terms of the X's. That wouldn't make sense. Or we don't want to invest a negative amount into the bond. That means we would actually owe money on it. So it must be greater than or equal to zero. If it's greater than or equal to zero, it can be all real numbers. Our Y value, same thing. We don't want to put a negative amount into the GIC account. So we're not going to do that. We want to invest positive amounts or just not invest at all in the account. That is an option, is that we don't have to put money into one or the other, but it would be potentially nice to mix it up for some of the values for sure. And we're going to see that there's a lot of values that require that at least some money goes into each. All right, here's what the inequality looks like. For the first account, we know that it was a 4% interest rate. So it's going to be 0.04 and then times the X, or the amount invested in the bond, plus the 0.05 or the 5% invested with the total of being Y. So this is essentially saying if I take a certain amount of money, which is X, and invest it at 4%, I'll earn a certain amount. If I take the GIC investment and I multiply it by the 0.05%, this will give us the amount that we earn in interest on the GIC. And then we want to earn at least $300 or more. So we can clearly see that the investment or the amount of interest we earn in the year should be greater than or equal to the 300 that is the target. All right, awesome. So this gives us the inequality that would represent this overall situation. So we could highlight this and say, hey, you know what? Great solution. But now what we want to do is we want to isolate this for Y to help us build out the graph algebraically. To do that, I'm going to subtract by the 0.04x and move it over. So 0.04x moves away. Now we're going to write it as 0.05 times y is greater than or equal to the negative 0.04 for the x plus the 300 that was already on that side. I'm going to divide both sides by 0.05. When I divide both sides by the 0.05, we'll do that to both terms here. So divide by 0.05, there we go. Because we're not dividing by a negative, we will not flip the inequality. It's only when we divide or multiply that we would change it. I'm going to write this as y is greater than or equal to this negative 0.4 over 0.05 gives me 0.8 negative for the x. 300 divided by 0.5 gives us positive, and 0.05 gives us 6,000. Now, again, as soon as you get it in this form where y is isolated and you have the constant term right below this, that you have the y-intercept. That's really, really important. Okay, now let's sketch this out on the graph here. If this is our y's and this is our x's, just as they normally are, I'm going to go up here and put that this point here, our original point, is 0 for x and 6,000 for y, aka the y-intercept. Now, we could also interpret this in the following way. If it's the y-intercept, the y's were the total amount that were invested in the GIC, meaning that could be an amount that we invest in the GIC, and then 0 would be the amount invested in the bond. That's one option that could be available to us. Now, in order to build out the graph, algebraically, we want to solve for the x-intercept. To solve for the x-intercept, we're almost going to do what we did last time and just take this equation here, the one that's the original inequality, and we're going to plug in 0 for y, eliminating the y term, and then we can isolate this for x. So let's do that below here. We're going to take this and go, okay, for the x-intercept, we'll take the 0.04x plus 0.05 times 0, because we're going to try and solve for our x-intercept, is greater than or equal to 300. This will mean 0.04 is greater than, and I need an x there, 0.04x is greater than or equal to 300. We're going to divide both sides by the 0.04 in order to isolate the x. And therefore, x is greater than or equal to 300 divided by 0.04. This is going to end up giving us, I believe, 7,500. There we go. So there's the inequality that satisfies this for the x values, or the x-intercept. And so we're going to go down here, and now we're going to put in that this piece here is going to be our x-intercept. It is 7,500 here. 0 for the y. So this is another option. We could invest all of the money, or take all of the money that we have in savings and put it into the bond account and put 0 into the GIC, and that would also give us this 300. Now we're going to draw our boundary line, and it's going to be solid. The reason it's going to be solid is because it represents the all the possible options, including the options that will equal 300. And in this case, because the inequality said, hey, we want the options where the bond will at least make 300 or be greater, we now want to look at this and say, hey, all of this or the solutions are defined by all the values outside the inequality like this. And so you want to highlight this region here where it includes the boundary line. So you're totally fine to include that boundary line in your highlighting or in your shading. And it must be all the values that are beyond this in order to satisfy this overall inequality. Because again, we wanted to make a minimum of $300, which is the boundary line. Once we get past the boundary line, now we can make things like $400, $500, $600, whatever it might be. Obviously, that's going to require more money out of your account, but to make that minimum of 300, this must be the situation. Okay, now let's sketch our solution region. We did that, check mark. Now what we want to do is use a test point to verify our solution. To do this, let's just go over here and we're going to draw in a test point in the following way. Suppose I take, I don't know, let's say I go here. And I'm going to say that this is roughly about 5,000 for X. And then I'm going to kind of invent the Y value. Let's say this is about, I don't know, let's say 3,000. We'll see if this works. So 5,000 invested into the bond account, 3,000 invested into the GIC. We'll see if this satisfies this equation here or satisfies the inequality. Okay, going below, we're going to go and plug them into the original equation, 0.04 times the original value, which in this case was 5,000 for the X. For the Y, this is going to be 0.05 times the, what did we select for the value again, just to make sure? Oh yeah, 3,000. All right, 3,000 for this one. And then this is supposedly greater than or equal to the 300. Now, let's just do some math here. If I end up taking the 0.5, or let's start with the 0.4, if I take 0.04 and multiply it by 5,000, this is going to end up giving me, just to make sure I get it here, 5,000. I'm going to get 200 from this section plus 0.05 times the value of 3,000. This is going to give us 150, which is greater than or equal to 300. Let's just make sure we add up those values. 200 plus 150 is $350, which is greater than 300. Therefore, yes, this is a solution. We would put check mark, and we can say that 5,000 and 3,000, or 5,000 invested with bonds, 3,000 invested in the GIC, is a solution that satisfies this. And even just saying this is a solution is way more than enough. That's perfect for us. Awesome. All right, now here's where you want to go into your homework. As you can see, the parts where they deal with these economic trade-offs, they're very formulaic. In fact, you're doing the exact same steps every time. In terms of the graphing problems, you just need to make sure you have it in terms of y equals, or in terms of y being isolated on one side with your inequality symbol between, such that you can type it into your graphing calculator under your y equals mode. And then for my Casios and my TIs, you can select in your calculator the ability to sketch the region. So if it's going to be less than, you would go the lower triangle on my TIs. On the greater than or equal to, or the greater than, you can select the upper triangle. And then on the Casios, if you click type, arrow over, and then you select either greater than, less than, or whatever it may be, you can then make that overall inequality sketch the appropriate region. All right, good luck with the practice.